In the freezing November of 1939, British ships were dying in silence. No torpedo trails, no submarine periscopes, just sudden, catastrophic explosions that tore steel hulls apart like paper. The Admiralty was baffled. Captains reported feeling the deck shudder, then nothing, just cold North Sea water rushing in. Hitler boasted on German radio that Britain would be starved into submission by Christmas. His secret weapon, he claimed, was unstoppable. By late November, Britain had lost over 20 vessels to this phantom menace. The Thames estuary became a graveyard. Southampton's docks went silent. Liverpool's merchants refused to sail. The Ministry of Defense knew they were facing something unprecedented, something that conventional naval doctrine couldn't explain. Every traditional countermeasure, deeper channels, different routes, heavier escorts, failed utterly. On 23 November 1939, HMS Belfast, a brand-new town-class cruiser, struck one of these invisible killers in the Firth of Forth. The explosion broke her back. 3 years of repairs lay ahead. That same night, a German Heinkel 59 seaplane made a critical error. Flying through anti-aircraft fire over the Thames estuary near Shoeburyness, the pilot released his payload too early. The weapon landed on the mudflats at low tide, intact and visible. This was Britain's first chance to see Hitler's secret weapon up close. 2 officers from HMS Vernon, the Royal Navy's torpedo and mining school, were dispatched immediately. Lieutenant Commanders John Ouvry and Roger Lewis approached the device in darkness, knowing it could detonate at any moment. Lewis later recalled in declassified interviews that he could hear his own heartbeat louder than the waves. After hours of painstaking work, Lewis thrust his arm inside the casing and unscrewed the detonator. The magnetic mine's secret was finally exposed. Inside the casing was elegant German engineering, a sensitive magnetometer that detected distortions in the Earth's magnetic field. Every steel ship, by virtue of its construction, becomes a floating magnet. The hull accumulates magnetic charge from the Earth's field, from welding, from the engines, from simply sailing north or south. When a vessel passed overhead, the mine's sensor detected this magnetic anomaly and triggered 300 kilograms of high explosive. No contact necessary, no warning possible. Enter Charles Goodeve, a Canadian-born chemist and lieutenant commander in the Royal Naval Volunteer Reserve. Goodeve wasn't your typical naval officer. He'd been teaching physical chemistry at University College London when war broke out, and he joined HMS Vernon's mine design department because he understood electromagnetism in ways career sailors didn't. Looking at the recovered mine's mechanism, Goodeve saw not a weapon, but a physics problem. The Admiralty's initial solution was predictable: thicker hulls, degaussing stations on shore, perhaps non-magnetic ships built from aluminium. Goodeve dismissed all of it. Building new ships would take years Britain didn't have. Shore-based demagnetization couldn't keep up with the hundreds of vessels sailing daily. What Britain needed was a mobile solution, something simple enough to be fitted to any vessel at sea. Goodeve's idea was almost insultingly simple. If the ship's magnetic field triggered the mine, then create an opposite magnetic field to cancel it out. He proposed wrapping an electrical coil around the entire hull, bow to stern, port to starboard, and running a carefully calibrated current through it. The resulting electromagnetic field would neutralize the ship's magnetic signature, rendering it effectively invisible to the mine's sensors. The establishment thought he was mad. Admirals who'd spent 30 years at sea questioned how a university chemist could solve what naval engineers couldn't. The coils would add weight, the electrical systems might interfere with navigation. What if the current fluctuated? What if it didn't work at all? Goodeve faced what every innovator confronts: the institutional inertia of people who'd rather fail conventionally than succeed unconventionally. If you think history books have overlooked this, hit the like button right now to help us bring these untold British stories to light. Goodeve didn't argue, he experimented. In early December 1939, working alongside physicist Edward Bullard, he fitted the first prototype coils to a minesweeper at Portsmouth. The installation took 12 hours. Heavy copper cables, borrowed from a power station, were lashed along the outer hull. A car battery and a rheostat, a simple variable resistor, provided the current. The mathematics was basic electromagnetic theory, but no one had applied it at this scale before. On 19th December 1939, Goodeve's team conducted the first live test. They sailed the minesweeper directly over a recovered German magnetic mine rigged with recording equipment instead of explosives. The instruments measured magnetic field strength as the ship passed overhead. With the degaussing coils switched off, the mine's sensor registered a massive magnetic spike, more than enough to trigger detonation. Then they powered up Goodeve's system. The needle barely moved. The ship's magnetic signature had dropped to near zero. The mine's sensor registered nothing. It was as if a 1,200-ton steel vessel had simply vanished from the Earth's magnetic field. Goodeve termed the process degaussing, after the Gauss unit used to measure magnetic field strength, named, ironically, after German scientist Carl Gauss. But one successful test wasn't victory. Britain had over 2,000 merchant vessels and warships requiring protection. The Thames was still mined, Southampton couldn't function, and across the Channel the Wehrmacht was preparing its spring offensive. If Britain couldn't move supplies and troops safely by sea, the war would be lost by summer. Goodeve's next innovation was even more ingenious than degaussing itself. Installing coils took too long, 12 hours per ship. So he developed wiping, a technique where a vessel passed through a massive electromagnetic field generated by shore-based coils. This temporarily demagnetized the ship's hull, reducing its magnetic signature for several weeks. A ship could be wiped in under an hour. By April 1940, 10 degaussing stations were operational across Britain. But in late May, disaster struck again, not from German mines, but from German tanks. The Wehrmacht broke through at Sedan. The British Expeditionary Force was trapped at Dunkirk. Over 300,000 men needed evacuation from French beaches, and the route across the Channel was thick with magnetic mines. This was the moment Goodeve's invention proved its worth. From 26th May to 4th June 1940, in a 4-day marathon session, Goodeve's teams wiped 400 ships. Destroyers, minesweepers, fishing trawlers, pleasure yachts, anything that could float was processed through the degaussing stations at Dover, Portsmouth, and Harwich. The operation ran 24 hours continuously. Crews worked in shifts, ships queued for miles. The numbers are staggering. 400 ships in 96 hours meant one vessel completed every 14 minutes. It was naval logistics at a scale and speed never attempted before. And it worked. During Operation Dynamo, only 6 British vessels were lost to magnetic mines out of over 900 trips across the Channel. Without degaussing, the Dunkirk evacuation would have been a bloodbath. The technical elegance of Goodeve's system lay in its simplicity.
It required no rare materials, no advanced manufacturing, no specialized training. A ship's electrician could maintain the coils. The current draw was minimal, less than a few car headlamps. The system could be adjusted based on latitude because the Earth's magnetic field varies from north to south. Goodeve even designed polarity reversal switches for ships operating in southern hemispheres. By war's end, virtually every Allied vessel, British, American, Canadian, Australian, sailed with degaussing protection. The system saved thousands of ships and tens of thousands of lives. German magnetic mines, once Hitler's unstoppable secret weapon, became little more than expensive scrap metal littering the seabed. All because a chemistry lecturer understood that you don't fight physics, you use physics. Yet Goodeve's recognition came grudgingly. He was awarded an OBE in 1945, promoted within the Navy's research division, and eventually knighted after the war. But he never received the public acclaim given to radar developers or Enigma codebreakers. His work was classified until the 1970s. The official histories barely mention him. When he died in 1980, the obituaries focused on his post-war steel industry work, not the invention that saved Britain. There's a bitter irony here. Goodeve's degaussing was arguably more immediately impactful than any other British wartime innovation. Radar won battles, Enigma decryption provided intelligence, but degaussing kept the sea lanes open, and without those lanes, Britain would have starved before radar or codebreaking mattered. It was the unsexy, unglamorous technology that made everything else possible. The German naval archives, declassified in the 1980s, reveal the enemy's perspective. By mid-1940, German intelligence knew the Allies had countered the magnetic mine. Kriegsmarine reports called it a catastrophic failure of offensive mining strategy. They'd invested millions of Reichsmarks and thousands of engineering hours into a weapon system neutralized by copper wire and a car battery. The psychological impact on German naval planners was devastating. Goodeve went on to develop other weapons during the war: the Hedgehog anti-submarine mortar, the Oerlikon 20mm cannon production in Britain, advanced minesweeping techniques. But nothing matched the elegance and immediate necessity of degaussing. It was pure applied physics solving an existential threat, and it worked the first time. Today, every modern warship still carries degaussing equipment. The technology has evolved: solid-state electronics, computer-controlled field adjustments, integration with stealth systems. But the fundamental principle remains Goodeve's: create an equal and opposite magnetic field, cancel the signature, become invisible to magnetic sensors. Simple physics, executed brilliantly under imaginable pressure. Tell us in the comments, is this man the greatest engineer Britain forgot? I read every single one of your responses. The story of Charles Goodeve and the magnetic mine is a reminder that the most critical innovations often come from outside the establishment. The naval officers couldn't see the solution because they were thinking like sailors. Goodeve, trained in electrochemistry and physics, saw a magnetic field problem, not a naval warfare problem. His intellectual toolkit was different, and that made all the difference. It's also a story about urgency. Goodeve developed degaussing in weeks, not years. There were no lengthy procurement processes, no committee reviews, no prototype approval chains. Britain was losing ships daily. The Navy gave him resources and freedom, and he delivered. Modern defense procurement could learn from that desperation-driven efficiency. If you walk along the Thames at Shoeburyness today, you can stand near where that German mine landed in the mud. There's no monument, no historical marker, just grey water and grey sky. But beneath that unremarkable shoreline, Britain's survival hinged on a piece of German engineering that accidentally fell from a Heinkel's bomb bay and landed intact. Goodeve didn't just outsmart Hitler's secret weapon. He demonstrated that scientific thinking, applied rapidly and decisively, could overcome any technological threat. He proved that sometimes the most sophisticated problems require elegant, simple solutions, and he saved Britain at the moment Britain most needed saving. Subscribe for more deep dives into the hidden history of British innovation, and watch this next video on how British scientists cracked the Enigma code to see how the story continues.